In this lesson, I'll show you how to solve electrical problems by the Laplace transform. This is question number 2. Specifically in this question, we'll look at series RC circuits with a DC source. The question reads, a capacitor has an initial charge of 35 volts with the polarity as marked in the diagram below. Find the current if the switch is closed at t is equal to 0. To be successful with this question, we'll need to know Kirchhoff's voltage law, and this was mentioned in question number 1. It states that the sum of the voltage that drops across the resistor, an inductor, and a capacitor in an electrical circuit must be the same as the voltage source applied to the RLC circuit. And the voltage source being applied here is 115 volts. So we have 115 is equal to the drop in voltage here, which I'll represent as R times I, resistance times the instantaneous current, plus the voltage across this capacitor. The voltage across this capacitor is represented by this equation, where we have 1 over the capacitance times the integral of I between 0 and t. So I'll take this and place it right here, 1 over c times the integral between 0 and t times I dt. Also, according to the question, a capacitor has an initial charge of 35 volts. So I'll need to subtract this by 35. So this number right here is technically the voltage of the capacitance. Now that we've written our equation, I can take minus 35 and bring it over to the other side, where we have 115 plus 35, that's a total of 150, is equal to the resistance given as 12 ohms times the current I plus 1 over 40 microfarads. That needs to be converted into farads. So 1 over 40 times 10 to the power of negative 6 times the integral between 0 and t I dt. Next, we have to take the Laplace of each individual term. Starting with the one on the left, we'll take the Laplace transform of 150. That's equal to the Laplace transform of 12i, which is 12 times the transform of I. Pulled out that 12 and took the Laplace transform of I only. Now I need to take the Laplace transform of this integral. First, I'll evaluate what 1 over 40 times 10 to the power of negative 6 is. 1 over 40 times 10 to the power of negative 6 gives us 25,000. So this can be replaced with 25,000. And we did a video where I took the Laplace transform of an integral, and we found out that it is equal to 1 over s times the Laplace transform of the independent variable. In our case, it's I. So I'll take this number and multiply it by 1 over s times the Laplace transform of I. And I'll substitute that right here. So I have plus 25,000 over s times the Laplace transform of I. Next, I'll try to isolate for the transform of I, and at the same time, this part will equal to 1 over s times 150. And in case you're curious, I'm using the table that I have over here, where if I take the Laplace transform of a constant, I end up with 1 over s, and multiplying 150 by that gives us 150 over s. This is equal to, factoring out the Laplace transform of I get 12 plus 25,000 over s, close bracket. Now coming up with a common denominator, we'll end up with an s that's shared by both terms and the letter s beside the 12. So I have 150 over s is equal to the Laplace transform of this factor, which I'll divide both sides by now. And if I do divide both sides, this s and this s will cancel out, leaving me with 150 over 12s plus 25,000. I need to now model this with a known Laplace transform found in this table. In question number 1, we used this, and it turns out that we're going to use it again. 1 over s minus a models what we have here, sort of. In fact, if I factor out a 12 from both of these terms, and dividing 25,000 by 12 gives us 2,083. 2,083 approximately. The next thing that I have to do is make sure that this looks like one of the expressions found in this table, which is a list of known Laplace transforms. And as you can tell, this looks like number 9. Well, almost. We have 1 over s minus a. A couple of issues. We have an s, which is good, but there's no minus, but we can change it into minus. I'll write it as 150 divided by 12 times 1 over s minus negative 2083. Now we have a definitive value of a, which is negative 2083. And I can write it as e to the power of negative 2083 times t, because I'm trying to model that, multiply to 150 divided by 12. 150 divided by 12 is equal to 25 over 2, or in other words, 12.5, is equal to my current.